Hi everyone and welcome into the webinar. My name's Keaton Anderson and I'm a Senior Manager of Customer Solutions with Avnet. I'm one of the speakers for today's event and I'm also going to act as the moderator. Today we're going to talk about how to unleash the power of Vision AI and accelerate Edge AI solutions with the Renesas RZV MPUs. But before we dive too deep into the content, I'd like to take a moment to introduce today's speakers. Jason Acevedo is a Senior Digital Field Application Engineer with Renesas. He's going to give an overview of the Renesas family of MPUs and talk about some of their value. Next, Lucas Keller is an embedded software engineer with the TRIA team, and he's going to talk about some of the applications that have been enabled with the RZ board V2L. After that, I'm going to tell you a little bit about IoT Connect before I hand it off to my colleague Stephen Detloff, who's an IoT Solutions Manager with Avnet. He's going to walk us through a Vision AI use case with the RZ board V2L and IoT Connect and show you just how quickly you can get going with our quick start. Finally, at the end of the event, we will have a Q&A availability, so please put your questions in the chat as we go along. To get things started, I'm going to hand it over to Jason, who's going to talk a little bit more about the Renesas RZ/V MPUs. Jason, over to you.
All right. Thank you all for joining us today. My name is Jason Acevedo, and I'm going to provide you with a brief overview of what Renesas has to offer, including the RZ V2L, which we'll be using today. So to start things off, for those that may not be familiar with Renesas, I wanted to show you a one-slide overview of the breadth of products that Renesas has to offer. We have a broad portfolio of microcontrollers and microprocessors covering the full range from low-power 16-bit microcontrollers to multi-core gigahertz microprocessors. We also have a number of analog and power devices, as well as sensors, timing, and wireless connectivity products. For today, we're going to be focusing on the RZ product family, which is our SoC-based product family. In the RZ product family, we have divided it into 5 subcategories, focusing on HMI, IoT, industrial networking, and industrial motor control. And the one we'll be focusing on today is the RZV family, which is focused on Vision AI. So what is the RZV family? Basically, the RZV family is a family of SoC devices designed for embedded Vision AI applications. These devices integrate a Renesas-developed AI accelerator, which we refer to as the DRP AI. This DRP AI hardware block was designed to provide a scalable, very power-efficient Vision AI solution for a broad range of applications. So now let's take a little bit of a closer look at what the DRP AI is. The DRP AI hardware block is basically a dynamically reprogrammable logic block, or DRP, tied to an AI Mac. With this configuration, we are able to divide the AI model into its various processing pieces and execute each of those pieces on a hardware block that is specifically designed for that computational logic. For example, the DRP block can be reconfigured on the fly to process the pooling, softmax, and other functions, while in parallel, the convolution layers are being run on the AI Mac. This enables the device to achieve very efficient processing of the AI algorithms. This efficiency then translates into higher performance and/or lower power. In addition to the DRP AI hardware block, there is also a software piece that we refer to as the DRP AI translator, or DRP AI TVM. This translating software enables typical AI models to take advantage of the DRP AI unique hardware architecture. So let's take a quick look at the performance and scalability that this DRP AI hardware block brings to the RZV product family. So here we have a brief video showing a side-by-side comparison of one of the RZV devices versus a traditional GPU. In this case, you can see that the DRP AI hardware device, the RZV2H, is able to achieve a faster frame rate of roughly 45 to 49 frames per second versus the traditional GPU running at roughly 21 frames per second. The other thing to note is that while both of these systems are executing the same AI model, The DRPAI device, the V2H, is running at 54 Celsius without a heat sink or fan, so there's no thermal management on this device. Whereas the GPU is also running at roughly 52 or 54 degrees Celsius, has a fan and a heat sink. So looking at what that means in terms of actual power consumption, here this table on the right, you can see that the DRPAI device is able to achieve its 5.3 millisecond inferencing time with roughly 1 watt of power consumption, whereas the GPU, which is taking 36.5 milliseconds for its inferencing time, is requiring 14.2 watts of power consumption. Looking at the scalability of the RZ family of products, you can see we have a number of devices ranging from some entry-level AI performance with the RZ V2L, going up to some higher performance with the RZ V2H. In comparing the inferencing time with different models, you can see that there is a range of performance that can be achieved with the differing products in the RZV family. Looking at a more detailed breakdown of different products in the RZV family, you can see that they scale from 0.4 tops all the way up to 80 tops in AI performance. They also come with a varying number of primary and secondary cores, GPU performance, display interfaces, camera interfaces, and other such peripheral mixes to enable you to choose the best product to meet your needs. Briefly, I wanted to touch base on the DRPAI software and the AI model development flow. For the RZ product family, the AI development flow starts off very traditionally. It starts off with data collection, annotation of that data, model development, training, and evaluation, which is what you would typically expect to see for a vision AI related application. All of this is done in the cloud. Once you've got a model in a typical format such as Onyx, TensorFlow, or PyTorch, that model is then fed into the DRP AI translator, or TVM, which then converts that model into code that will take advantage of the unique DRP AI hardware in the RZV device. That code is then ready to be put onto your device and run your application. This slide shows a little more detail in that process. So not only does the TVM change the model into code that takes advantage of the specific AI hardware quantization level, but it can also be used for pruning and retraining of the model in order to achieve higher performance. So what resources does Renesas have to help you get started? So Renesas has a number of ready-to-deploy AI applications, pre-built, pre-trained, and ready to enable you to quickly get up and running with a similar type of application to what you may be looking for. All of these models are available open source on GitHub with the training sets and all the details needed to modify them for your specific application. In addition to the software, we also have a number of hardware development kits and prototype boards that can be used for evaluation and development. The board we'll be using today is the RZ board. This has the RZ V2L device integrated into it. The RZ V2L is a dual-core A55 SoC running at 1.2 gigahertz. The RZ board is a Raspberry Pi form factor single board computer. It has 2 gigabits of DDR RAM, 32 gigabits of eMMC flash, 16 megabits of QSPI flash, and a micro SD slot, gigabit Ethernet, Wi-Fi, Bluetooth, USB, CAN FD, MIPI DSI, and HDMI display interfaces, as well as a MIPI CSI camera interface and a 3.5 millimeter stereo audio jack. That concludes my section of the presentation, and I will hand it off now. Thank you.
Hi everyone, Lucas Keller here with TRIA. I'd like to thank Jason for introducing the RZV family and the RZ board V2L. And today I'm going to talk a little bit about TRIA, our single board computers, development kits, and SOMs, and show some great demos that we've built out that are powered by OZY Connect. So first, who are we? TRIA is an AVNet company, one of the largest global SOM and COM manufacturers. In other words, a world leader in the design and manufacturing of embedded computing. We help OEMs to embed compute capabilities into their products by offering them a variety of off-the-shelf compute modules like SOMs or COMs or single-board computers or even custom designs. And we do that with our in-house design and global manufacturing footprint. So while the brand Tria may have only launched earlier this year in July, in reality, we're an Avnet company filled with people that have decades of experience in the embedded compute space. Today, I'm mostly going to be talking about the single-board computer and system-on-module form factors, and that's because if you're trying to leverage the RZ family of products here at Tria, you're going to be using the RZ board V2L, the single-board computer form factor, or the mass production units, the G2L, V2L, or G2UL SMART modules. Of course, based upon MOQ, we can talk about custom designs. Maybe you want to add a port, drop a port, or extend battery capabilities onto your RZ board. Just come and talk to us about that. And lastly, don't forget that Renesas also offers evaluation kits that can be powered with IoT Connect as well. So here's how we break down the product portfolio at Tria. You have the standard compute on module form factor. This is previously MSC or Avnet embedded products, if you're familiar. These are industry standard form factors for higher volume use cases. There's the application optimized boards, previously AES or advanced application group products. These are proprietary form factors and usually lower MOQ, like RZ board would fall under this category. And then lastly, there's development kits, also under the AES or advanced application group products. These are a good starting point for the mass market. But now back to RZ board V2L. For example, why RZ board V2L? Well, our intention was to facilitate development of vision AI applications. And that's because many of these applications have requirements around energy efficiency, reducing total network bandwidth, or privacy. And we believe that the Renesas V2L SoC really leans into these requirements. That's because of the DRP AI accelerator, for example, being efficient but capable of running some of the most popular AI algorithms for vision, like YOLO or ResNet, and leveraging those, for example, surveillance or monitoring oriented solutions, or because of the onboard H.264 encode decode unit, the GPU, or the image scaling unit. This lets you use the RZ board V2L as a generic computer. Plug in a monitor of choice or a MIPI DSI display. Beyond that, because of its form factor, there's a vast array of hardware expansion options available online that you can get started with right now. Lastly, one of my personal favorite things about this board is the onboard Cortex M33 core. That core is capable of running bare metal or FreeRTOS for motor control, which means that you have the capabilities of running generic computing, motor control, and AI all on one board, which really reduces the complexity and latency of robotics applications. So let me show you some of these applications that I've built out with RZ board V2L and IoT Connect. So first, probably my favorite reference design of all time, RZ Buddy. It's a smart treat dispenser that allows you to monitor and train your pet while you're away from home. It's powered by RZ board V2L and IoT Connect. It runs real-time YOLO, Linux and FreeRTOS in parallel. You can control and monitor via IoT Connect, and it's all open source hardware and software. So if you're interested in figuring out how to build this or use it as a reference design, it's all open source on GitHub. Next, the Spark demo, an open source reference design for edge AI monitoring and analytics. Spark uses a custom CNN to gather real-time parking occupancy information that is then streamed to IoT Connect for analytics and monitoring purposes. The simple design is capable of monitoring around 200 parking spaces in real time. Of course, being powered by IoT Connect means you can easily do OTA model or even security updates to your fleet. Businesses with sensitive, privacy-oriented requirements may opt to only send critical business analytics data, not the entire image stream through their network. Of course, the reference designs shown so far have been pretty specific, and your business requirements may be different, and that's where the last demo suite comes through. This next demonstration is a subset of the Model Zoo, a suite of AI applications Renesas built out to run on the RZV family. What's amazing about the Model Zoo is not just that there are many reference AI applications that also contain pre-trained models, but that these applications are built with different data pipelines, different models, sometimes even multi-stage models, and different AI backends for DRP AI. So this Model Zoo does a great job to provide insights on the edge deployment process and the design choices that come with Vision AI. So in front of you, you've got a couple safety-oriented models with the fall detection and hard hat detection, but also some other surveillance-oriented models like head counting, a driver monitoring system, or human gaze detection. Well, that wraps up the demo material I have to show. So I'm going to close out here by providing references on our Renesas-based dev kits, SBCs, and SOMs. On the left here, as seen previously, the RZ board V2L and its generic computing / HMI focused siblings, the G2L and the lower powered G2UL, just now coming into mass production. On the right, the Raisin board, another edge AI oriented device that has some great reference designs for using AI in relation to IMU or audio data, like classifying machine health through vibrations. Lastly, of note, the G3E and G3L compute modules are scheduled for 2025. These modules support low power modes and many interfaces, so they're great for IoT edge applications. That's all I have to talk about today, so thanks for listening, and now on to Keaton to talk to IoT Connect.
Perfect, thanks Lucas. That was an excellent overview of the RZ board V2L and some of the ways that it can be enabled. I'm going to talk a little bit about IoT Connect, but before I dive too deep into that, let me talk a little bit about who Avnet is. So Avnet's a global technology distributor. We've been in business for over 100 years. We have employees worldwide. And I think if you typically tend to think of Avnet, you think of us mostly for our supply chain services. And that's true. That's still our bread and butter. We do that very well. But one of the things we're most proud about is that over the past couple of years, we've made some significant investments that we really feel like has given us some unmatched capabilities in the IoT space. So companies like SoftWeb Solutions, Witekio, Tria, they enable us to do things like embedded software design or cloud and application development, embedded boards and modules. And one of the reasons that this is needed is because IoT requires multiple engineering disciplines to be able to create a full solution. So in this example, going from left to right, the first thing we'll start with is that hardware and firmware. So this could be an example of where that RZ board could plug in. Maybe I need to be able to do some level of vision AI, or I want to be able to track an industrial manufacturing arm to see if it's performing within maintenance specs. Then after I have that data, I'll need to connect it into the cloud. And then last but not least, I'll want to do some sort of user backend and experience. So this could be things like a mobile application, a web application. But one of the things that you'll notice is that in order to build out this entire solution, I need multiple different engineers to be able to work together. I need someone who's an expert at that hardware and firmware development. I need someone who's able to have cloud expertise, who knows how to build a backend or a user experience. And so this is one of the reasons why Avnet has developed IoT Connect. We want to provide a single place that all these disciplines can be able to come together to build IoT solutions. So how does this look in practice? So IoT Connect wants to take things like a connected manufacturing plant or an industrial gateway, and we want to extract business insights out of them. So in that example, that industrial manufacturing plant, maybe I want to be able to make sure that those devices aren't running hot. And if they are, maybe I send out someone to do predictive maintenance before we go line down. Additionally, maybe I want to do something like site monitoring, where I can be able to watch and have a warning zone to say, hey, if a worker goes too close to a machine, I want to shut that down. I want to try to do some preventative worker safety to make sure that we're taking care of our employees. And how this actually comes together is it's built on top of AWS services, and it creates a single pane of glass web experience. So it enables you to do things like manage your devices and view and analyze device data. And what this means is that you don't have to spend the time figuring out, hey, what AWS service do I need to call in order to be able to add a user to my environment? Instead, you can really start to rapidly accelerate your development by just adding your devices in and getting meaningful business insights out of them as soon as possible. So let's take a look at this with the RZ board V2L with a Vision AI use case. The RZ board is already pre-configured within IoT Connect, and Steven's going to walk through the quick start in terms of how you can be able to rapidly get that board onboarded into our ecosystem. And then we also have a pre-configured dashboard that enables you to do Vision AI and be able to switch between multiple models in a very quick manner. And so what you can start to be able to do with this is within a matter of minutes, maybe an hour, you can get this board connected into IoT Connect, have a dashboard already built out for you, and start being able to get real meaningful insights and use that vision model in this example to be able to start to do some really interesting things. So I'm going to jump into IoT Connect and just quickly showcase an example of how this looks like on the platform. Okay, so when I first jump into IoT Connect, this is an example of what it might look like. And what we've tried to create here is kind of a base user experience that gives you some information you might need. So things like device to cloud messages, if any rules have been violated, how many users you had, the number of devices, all of that's kind of captured in your base dashboard. But one of the things that will probably happen for you is that you'll need something more particular for your application. And so we've made the ability to create dynamic dashboards. And what that means is you can be able to take some of these pre-built widgets that we have and drag them onto the canvas. So maybe you need, say, a device tracker to see where your devices are located. You need to be able to pull in a particular image, or you need a gauge chart. All of those are available and you can drag them right on the canvas. Once you're done and happy with how this dashboard's coming together, you can click Save, and that enables you to be able to do a couple things like share this dashboard out. So if I wanted to send this to someone I'm working with and say, hey, look at the device data that's coming through, I could be able to pull that up, and that would share over that dashboard I've just built and any device data that's flowing through. It's obviously blank on this one because I just created this. I haven't linked it to any devices. But it is one of the ways that you can be able to quickly showcase data. Additionally, you can then go and both export and import with this. And we're going to use that import function later as part of the quick start in order to be able to give you a base dashboard to work with for the RZ board V2L. So just keep that in mind. We're going to be using this a little bit later. Let's talk a little bit about how IoT Connect handles segmentation. So entities are our way of doing both user and device segmentation. So in this example, you'll see that I've set up, let's say I have 3 different manufacturing offices or plants, and I can separate them by location. So in this case, I have a Denver office, a Paris office, and a New York office. And again, these are just examples that may not be realistic based on your company. We also then have the ability to further segment on those. So in this example, you'll see that I have 3 devices in Denver and 1 device in New York, but maybe I want to segment by the floors that I have as well. I can create sub-entities under that location in order to be able to add multiple layers of this. And so one of the ways you might use this is I want to track a particular set of devices on the first floor in my Denver office. Maybe I want to be able to pilot when I have a new AI model that I want to deploy to them. Having the ability to segment both by location and then again by floor enables you to start to engage with your devices on a smaller level or a big level if you need to. Additionally, we have the ability to do users and permissions. I won't go a ton here, but just know that you can set the level of permissions to what a user might need. And then let's take a look at how devices come together with IoT Connect. So IoT Connect has the ability to connect to a wide array of devices. So on this screen alone, you'll see we have the ability to connect to things like Greengrass devices, LoRa devices. Really, if you can think of it, we can connect with it. And so let's take a look at how that comes together from a device perspective. So I have a template that I've created. I'm going to go ahead and show you real quick. And it is this demo device template right here. And I've created 3 different attributes for this. So I've created one that's a temperature one, that is an integer. I've created one that's a current for the device, given in amps, that's a decimal. And then I have a person detection one, and this is a Boolean check. So it's going to be either true or false to say, do I detected a person there? And keep in mind, one of the applications with the RZ board V2L is that Vision AI, and we're going to be using a model to detect different images, and with a live video feed, we could very easily detect a person. And once I've had this template created, and that kind of lets IoT Connect know what values to be expecting and what that data coming through is going to look like, I then can create a device with it. And so in this case, you'll notice I've set up this demo device 1, and it has those different attributes. So you can see here I have that current, person detection, and temperature. Once I'm happy and I have all the different values that I need in IoT Connect, I can start to do some interesting things with rules. So I'm going to take a look at this worker safety rule that I've created. And what this does is it enables us to be able to use the attributes to check and kind of do some feedback cycle on them. So if something happens, then do some actions. So in this case, I have a rule called worker safety. It's using that demo device template that I talked about before, and that severity level I've set to critical. And I'm actually going to zoom in this so it's a little easier to see. So with that, that person detection attribute that I talked about before, that's that Boolean check, I'm going to look to see if that becomes equal to true. So an example of this might be I have a manufacturing plant. I have a particular machine that I don't want any of my workers within. If someone goes within there and I have a camera that's watching it and I detect, hey, a person's in this zone that they really shouldn't be, then I could issue a shutdown command. So for that first floor entity, if I see that particular device that I'm monitoring, if someone's within too close, I can actually shut that device down right from within IoT Connect. And I've set this rule up just by default. That was a very easy, quick thing to say, is this parameter flipping from false to true? Yes, go ahead and do that shutdown. Additionally, I can do things like send out an email. I could do a push notification. I could do a webhook. All of those can be enabled out of the box within IoT Connect. And last but not least, I could add some different users that I might need to send a warning to and say, hey, something's gone wrong. Please address this immediately. So again, default out of the box with IoT Connect, you have the ability to immediately start getting some of those meaningful insights that we talked about from some of the data that you're getting from that board. And then last but not least, I just want to quickly show we do have the ability to push new AI models directly from IoT Connect. And so as the model is continually trained and improved, you can be able to then push that to the board and to the things to be able to improve your insights. And so it's a really great feedback cycle, again, all built from within the base experience of IoT Connect. And then last but not least, we do have the all of our API information, all of our SDK information directly from right within the tool. So you'll have everything that you need in order to be able to get started and developed. So with that, we're going to go through a particular example, and I'm going to hand it to my colleague, Stephen Detloff, who's going to talk a little bit about the quick start for the RZ board V2L and a Vision AI application use case. So Stephen, I'm going to hand it over to you.
Hey, thanks, Keaton. So again, my name is Stephen Detloff, and today I'll be walking through the demo portion of today's webinar, where I'll be going through a quick start guide we have in GitHub, which will allow us to connect the RZ board V2L to the IoT Connect platform, where we can activate various models and see the results in real time in our dynamic dashboarding feature. So with that, we'll move over to the GitHub and get started. You can find a link to the GitHub repository in the webinar platform, and it will also be provided in the collateral at the conclusion of this webinar. So once you follow the GitHub link, you should arrive at the rzboard_v2l.md file, and the title will be, as shown here, RZBoard V2L IoTC Quick Start Guide. And this is what we'll be going through today for the demo portion of the webinar. I already covered the goals for today, so I'm going to go ahead and skip the introduction section, but I will point out that this guide is written to be followed on a Windows 10 or 11 host machine, and obviously if you're using a Linux environment, you can adapt appropriately. I'll move down here to the hardware requirements section, and basically everything here should be pretty self-explanatory. You'll need a micro SD card, and you'll need a variety of cables that we'll use to connect the board to your PC, and additionally you'll need some I/O in the form of a USB webcam, and you'll need a micro HDMI to HDMI cable so you can view the output of the inferencing in real time. So once you've gathered all the requirements, and again you can follow these links, they're just generic search terms to Amazon, so you can find some of these items if you don't already have them. So again, once you have all these, we can move to section 3, which is the hardware setup section. So here we'll be connecting the various peripherals and I/O from the development board to your host PC. And I wanted to point out a couple items they should pay close attention to. First of all, make sure you do not connect the USB-C cable quite yet. You can connect it to the board, but don't provide power to it or connect to your PC, as we'll do that in a later step. And then additionally, I wanted to make note of the location of the TX ground and RX pins that you'll use to connect the serial to USB adapter, which are outlined here down in this red box. You'll also want to pay attention to the pins that you use to connect the 5-volt jumper wire. That'll be the leftmost UART here, and up to the top leftmost pin on the header on the RZ board. And then lastly, you'll want to take a look to make sure your boot configuration is in the right orientation, and that is configured with dip switch 1 in the on position and dip switch 2 in the off position. I'll go ahead and show what my board looks like here on the webcam, and you can see up in the top right corner I have my USB-C cable connected to the board but not yet connected to the PC, my micro HD to HDMI. You'll see I have my jumper wire, which I'll connect in just a moment, my serial to USB. I have my USB webcam plugged in here, and my Ethernet cable. This is the jumper wire I'm using. It's got a hook on it, so you can protrude this hook. I'm using that to connect the upper rightmost pin here to provide power. So once you have everything connected, we can move back to the GitHub guide, and we can look at the next section, which is section 4, about installing some software. So I've bullet pointed the 3 pieces of software I'll be using today. Balena Etcher to write the image to the SD card. We'll be using Git for Windows to have access to a bash shell, and we'll be using Python to support some of the scripting we'll be doing to help automate some of the onboarding process. One thing to point out, make sure you do add Python to the path variable, as if you don't, you might encounter some errors with some of the scripts. So make sure you just download all these. Here's the direct links, download and install those, and then we can work on doing the first step of flashing the image to the board in step 5 here. So the first step here is going to be downloading and extracting the zip file, which is the quick start package. You can right click on this link and save as. I do recommend saving it to the same project directory I've outlined here. That will make following the rest of this guide a little bit simpler. So just go ahead, again, right click, save as, download and extract. I'm going to make my window just a tiny bit smaller so I can show you what I've done here. You can see that's the directory I've outlined. Here is the zip file I downloaded, and then I extracted the contents right into the same directory as well. So once you have that downloaded and extracted, we can load the Balena Etcher application to flash that WIC file that was extracted to the SD card. So we'll hit Flash from File. We'll go ahead and select the .wic file that's outlined here, hit Open. And you'll want to make sure you've got your SD card selected and not a local partition. So here it is, 16 gigabyte card, and we can hit the flash button here to get started. I will note that this flash process will take a little while, and then also at the very end it will want to do a verification. Depending on the permissions you have in your computer, the verification process may fail. You can safely ignore that. Or when the time comes, there's an option to skip that verification. So as long as the flashing makes it to 100%, you should be fine. So I'm going to go ahead and pause for just a moment and let this flashing complete. Okay, you can see my flashing process is just about finishing up. And once it wraps up, it'll give me an option to do the verification or skip that step. And like I mentioned earlier, I'm just going to go ahead and hit skip. And then we are done. The flashing is complete. And we have written the WIC file to our SD card. So at this point we can close Balena Etcher, and then we can return to the guide here, and I'll move down here to step 6 regarding configuring the Flash utility. So we're going to be downloading and configuring the Flash utility. We're actually going to be cloning it from a GitHub repository. So the best way to do this is to navigate to that folder that we saved the initial zip file in, which you can see here on the right. You can right click, and if you installed Git, you should have an option to open a Git bash from here. So go ahead and do that option, and it should open up a window such as this, and you should be in this directory here. This makes it easier, so we can just copy paste some commands in here. So the first thing we're going to do is we're going to clone the repository that contains the flashing utility. So you can just copy that, paste, hit enter, and this will go ahead and extract the latest version from our GitHub site. And then if you have a fresh installation of Python along with this, you'll also need to install some additional utilities. Again, you can just hit copy here. Those are documented in the Flash utility folder. So you can go ahead and just paste this in here, and then we'll automatically go ahead and install some utilities if you don't have those already installed. At this point, we're ready to go. We're ready to actually connect it and flash the bootloader or the boot utility there. By using this command here, we can just paste this one string in here. The one thing you will have to know for this to work is that we are going to be specifying a COM port. You'll notice here it's just listed as 00. You'll want to open your device manager in Windows. You can just press the Windows key and start typing device manager. And when that comes up, look under the port section and look for your USB to serial or UART bridge adapter. And you'll see mine is COM10. So when I go ahead and copy this, I can paste this down here, and then I'm just going to hit the left arrow, back arrow until I arrive at this section here where there's the COM port, and just change this to COM10. And then I'm going to hit enter. And at this point, it's ready to write the image, and it says please power on the board and make sure boot 2 is strapped. And that was what we already did by setting the boot switches earlier. So at this point, we're at step 6, and this is where we're going to connect that USB cable to the PC. So, initially we had connected that to the board. We'll want to connect to the other end to the PC there, and then we'll want to actually press the power button on the board. So the power button is located, I'll pull up the image here again, right next to the USB-C adapter. It's this small button right here. So if you press and hold this for about 1.5 seconds, you'll see we get some lights that come on the board, and you'll notice that we get some movement down here where it starts to say flashing bootloader. This is going to take quite a bit of time, up to 5 minutes or so. So again, I'm going to go ahead and pause this and resume when this flashing is done. Okay, so it's been about 5 minutes, and it says done flashing the bootloader, and I've been returned to a prompt. So we've completed steps 6 and 7 here as this portion of the guide. And so once it's done now, we're going to want to go ahead and remove the USB-C power again and that jumper wire. So I recommend doing that in this order. Remove the USB-C cable from your PC. And then we're going to want to also remove that jumper wire. And I'll bring up an image of my board again too, just so you can take a look at what I'm doing. So I've removed the PC end of the USB-C cable, and now I'm going to go ahead and remove the jumper wire here. You can leave the other end on, it's no big deal. And then importantly, now we're going to tell the board to boot from the SD card now that we have a bootloader in there. And we're going to do that by switching the dip switches, basically just going to invert both positions. So 1 is going to now be in the off position, and 2 is going to be in the on position. I found the best tool to use for this is just like a bent paper clip. It's because these little dip switches are very hard to move. So grab one of these, flip those dip switches to the positions outlined here in the guide. At this point, you'll want to take the SD card out of your PC and put it into the SD card slot on the board. And that is located right on the end here. You can kind of see it on the end of the board right here. So we'll pull it out of the computer. We'll put that into the board. We'll set the dip switches, and then we're going to reconnect the USB-C power. So we'll put it back to the PC, and then we'll press the button for about another 1.5 seconds to turn the board back on. And at that point, we'll be moving to section 7. So as you can see, I have a blue flashing light on the board, which means I'm powered back up. We're good to go, it's booted. And the next step here is to download this configuration script. So I'm going to go ahead and just hide this window again. And here we're downloading this onboard.zip package. You can just go ahead, right click on this, save as, and again, put it in the same directory as everything else that we've been working on today, right into that RZ board V2L directory. So I'll just go ahead and go here, save that file right to there, and you'll see that's going to appear here in just a moment. So this contains some scripts that we'll be using to help automate the onboarding of this device to the IoT Connect platform. It performs a variety of tasks, including moving some of the model files over, moving some device certificates around, setting some file permissions. A lot of stuff you normally have to do manually. We've just automated it all with this zip file here. So once it's downloaded, make sure you extract it. I like to use 7-zip and just do extract here. You can also just use the built-in Windows, but just make sure all the files are directly in this onboard folder, and it's not two directories down, because sometimes Windows likes to do that. So make sure you just have it in an onboard folder here like this. And with that, we have the configuration script ready to go, and we'll be using that in a future step. But for now, we'll move to the cloud account setup piece. So if you don't already have an IoT Connect account, we do offer a free trial. As a reminder, IoT Connect runs on the major hyperscale clouds, being AWS and Azure. This guide is specifically written to run on the AWS version of IoT Connect. So you can just follow this link here where you can sign up for a free trial. There's no credit card required. You can just fill out some basic information, including an email and some contact information, and you'll be able to get an account. Keep an eye out for 2 different emails. You'll have a welcome email, and then you'll also have an email that contains your temporary password. Sometimes that likes to go to the spam folder, so just double check. If you don't see it in your normal inbox, just check your spam folder there. If you want some additional information on this subscription, you can follow this link here. But assuming you've completed this step, we can move to section 9, where we're going to be importing a device template. And a device template is really just the way that we use to define the type of telemetry that the platform should expect to receive from any edge device. It also defines commands that we can send from the IoT Connect platform back down to that edge device. And that's all encompassed in this device template file that's saved in a JSON format. So you can go ahead and right-click on this link here and hit Save As. And this is going to save a pre-built device template that I've created for this demo. You can also create these from scratch. That's a little outside the scope for today. Just save it right in the root of the project folder we've been working in throughout the duration of this demo. And we'll see that show up over here as a JSON file. And we're ready to go. We have that device template. You can next follow the login link here to console.iotconnect.io, and this will take you into the main dashboard view, which is right here. And it'll probably prompt you to enter your credentials, so you'll want to log in here. And at this point, we're ready to import that device template. So we can do that by clicking over here on or hovering over the devices menu and then the device submenu. This will take a moment to load, and then at the bottom you can see all the different types of screens that are associated with operations on a device. And the first one we'll want to do is the templates. So we'll start from the far left and click templates. So we don't currently have a template in here at all, and we're going to go ahead and create one. So this is where you'd create one from scratch if you wanted to do that. I'm going to go ahead and hit the import button in the upper right here. And then I'm going to browse for the template file I just downloaded a moment ago. And again, it's in our root folder here. It's this device underscore template underscore rzboard underscore ai.json, hit open, and then I'm going to hit save. That's going to take that file and load it in here. And I can notice that we have 5 different attributes associated here. We have some versions, some CPU usage, memory usage. We'll see this later, but this is the data that we're going to be getting from the edge. Additionally, we have some commands that we can send down, and it's kind of a sneak preview for later, but we'll be able to turn on and off these various demos just using some commands being sent from the cloud, and control the onboard LED, just kind of another fun thing we can do. Next, we'll want to go to the devices menu. And in fact, I'm going to switch back to the guide first. So here, I just wanted to recap. We downloaded this JSON, we logged into the portal, and then we imported that into our instance. And with that, we can move to section 10 here, where we're going to create a device. So you saw me already flip over to that device menu. So the steps are all outlined here in what we're going to be doing. I'm going to do that all in real time on the dashboard. But if you'd like to follow along at a later time, you can always return to this guide and follow these steps. So if I return back to the IoT Connect platform, I've already completed my template section. And here, I want to go to the devices menu. And now we don't have a device in here, so we need to create one. And this will be unique to the device that you have. So I'll start by clicking Create Device in the upper right corner. And this is going to give me a Create Device menu view here. I recommend using all the same text that I'm using here. I'm going to call my unique ID RZ board V2L. Obviously, if you had a plethora of devices, you'd want to create a unique name for each of one of your devices. But for the sake of simplicity and consistency throughout this guide, I'll be using RZ board V2L for both the unique ID and the device name. Again, the device name is more of the human readable version of the name. The unique ID is just that. It could be this plus some serial number if you're deploying a bunch of products in production. But I'll leave them both at RZ board V2L for now. Entity, Keaton touched on this a little bit earlier. If you created a new instance of IoT Connect, you're only going to have one entity. It's the one that's kind of default created when you create a free trial account. But just know you could have multiple entities to segment devices. And then the template is what we just imported a moment ago. RZ board AI is how it's abbreviated here. So we'll just select the only one that's available. And for the device certificate, we're going to auto-generate one, which is recommended. You could also use your own certificates, but it is recommended we auto-generate one. And with that, I'm going to go ahead and hit Save and View. So this will create a new device associated with the device template that I previously imported. So this device will now have all the same attributes and command capabilities that were defined in that device template. And you can see there's the template that it's been assigned to. And next, what we'll want to do is download some information. So we've created a device associated with a template, and now we're going to use this icon up here in the top right, which is going to download the device configuration. So this is going to take all the information about the device type, the template, how to connect to the specific platform, and roll it all up into one file. I'm going to go ahead and take this file, and it's also called IOTC deviceconfig.json. And we're actually going to want to put this in the onboard folder. So if you recall, I mentioned earlier, the onboard automates a lot of tasks. Well, some of the script is going to parse this file and automatically extract some necessary information. So I'm just going to go ahead and put it right into this onboard folder here and hit save. And then there's also another link here called connection info. And this is going to define how we actually connect to the specific IoT Connect platform. And it contains some things like pub and subtopics for AWS. But once you load this up, there'll be an icon here in the top right corner where you can download some information, including some device certificates. So you'll notice it's going to take the name that we called the device, RZ board v2l dash and then certificates.zip. And again, you'll want to put this directly into the onboard folder. So again, this is going to be part of the automated script that happens later. It's going to automatically transfer these. We don't need to extract it. Just make sure you save it into the onboard folder by clicking save there. And with that, I'm going to minimize this window and kind of return to the guide. So we just completed section 10, where we've gone through steps 1 through 9, ending with downloading both that device configuration, and we downloaded the RZ board certificates.zip both into that onboard folder. So again, that's outlined here. So once you've completed these steps, or you followed along with what I just walked through, we can move down here to section 11. So we need to connect to the board via SSH, and to do that we need to know its IP address so we can accurately connect to it. There's two main ways of finding out the IP address of the board. If you're at home or in an environment where you have access to the DHCP server, you might be able to find a DHCP lease associated with this specific host name, RZ board. If not, an alternative, an easier method potentially is to just connect to the board via serial terminal. So you can follow this link here for Google Chrome Labs.github.io. It's an in-browser serial terminal. So I'm just going to go ahead and middle click on this and open a new tab. You should have a window that looks like this, and we can just hit connect. And you'll notice that it gives you a pop-up and asks you which COM port to use. Again, you're going to want to look for the one that's associated with that adapter that you would have purchased. The UART bridge controller, in my case, could be called something serial adapter. Again, mine is, again, on COM 10. I knew that from earlier, so I can go ahead and hit connect. That says it's connected, so if I click in this window here, I see a little cursor. I can hit enter, and I have a login. The credentials to log in are root and avnet, and these are outlined directly in here in the guide. You'll see root and avnet for the password. And the next thing we're going to want to type is ifconfig, and that will give us the IP address associated with the interface eth0 to which our Ethernet port is connected. So ifconfig, and you'll see here that I have an IP address of 10.1.30.154 associated with my eth0. So that's the address I'll be using. You'll want to make note of this, copy it, put it in a notepad or just memorize it, because we'll be using that to enter into a script here in just a moment. So with that, I'm going to flip back over to the guide. We've just completed 11 on getting the IP address, which we'll be using for running the device setup script here. So to actually execute this script, we'll want to make sure we're in the onboard directory in git bash. So you can either double click on the onboard folder and then do another open git bash for here, or you can do like I did. I just did a cd and move to the onboard folder. But just make sure when you're in git bash, this is what you have visible. If I do an ls-l, I can see the script I'm going to be running here, and the next step is located in this directory, so I'm good to go. Go ahead and copy this, paste that in here. And the first thing it's going to do is prompt you for the target IP address. So this is the IP address we just obtained previously over in the serial terminal. Mine is ending in 154. So I can just go ahead and type 10.1.30.154. It's going to ask for the username. Again, the default is root, so you could just hit enter here. It'll go ahead and do some checking about keys. You're going to get an initial warning about the fingerprint not being known. Just hit yes here to continue to move forward. And then you're going to get prompted for the password for root, which is avnet 3 additional times. This is just the various copying and keys moving back and forth using SCP. So I'm going to type avnet, wait a couple seconds, type avnet again. And then lastly, one more avnet. And you can see it's moving like the public key over there. And then the next prompt we're going to get here is the full path for that IoTC device.config.json. If you recall, I mentioned to put that in the onboard folder. If you do that, there's nothing you have to do here other than hit enter. That's where it's going to default and look for it. Same for that certificates. As long as you put in the onboard folder, you could just hit enter. It'll look in those default locations. And at this point, it's going to go through and do some configuration. This is going to take just a few minutes to do, so I'm going to go ahead and pause and then resume when this is completed. And you'll know the script is completed when you get a message here about opening an SSH session. So we can just go in here and type yes. That will establish an SSH session to the board so we can directly connect to it. And then we can remotely execute the command here, iotc-application.sh, and that will actually start up the IoT Connect application on the board. So we'll go ahead and hit enter. And at this point, it's going to go ahead and spin up the application, connect to the IoT Connect platform, and begin pushing telemetry. So if we flip back over to here, after a short time, we should get a connected message. Here we go. I can see it coming through here as this board loads. We can see we do have it connected, so the board is successfully connecting. And with that, we can move to the next stage here, which is importing a dashboard. And the dashboards really help to visualize the data moving from the edge to the IoT Connect platform, and also give us a nice GUI to send commands back down. In the terminal here, we can see the script is running, and we can see some of the information that's being sent over, including, is there a script currently running, a model currently running? There is none. Memory usage, and this kind of information. So we can go visualize that directly in a dashboard. And similar to a device template, we can import pre-made dashboards. Just like we were importing a pre-made device template, we can import this pre-made dashboard here. So if I go ahead and right-click and save it as, I'm going to again save this directly into the V2L folder here next to my device template and hit save. And I'm going to go ahead in real time do these next 3 bullet points about importing the dashboard. So you can just kind of follow along with me live and then refer to this guide if you'd look to revisit this at a later time. So again, we're back here. We see this is connected. If I click live data, I can see some of the live MQTT data that's arriving to the platform. But I can go ahead and hit create dashboard here. And then I'm going to click the option for import a dashboard, and then browse. And then we'll want to make sure we click the dashboard export, not the device, the dashboard JSON, hit open. And we want to connect this dashboard to a specific device. Now you can imagine if you have a variety of devices and a variety of templates, we need to define which one should be pulling the data from. In our case, we only have the one template, so I'll just click the one that we imported earlier, and I only have one device on here. But you could have multiple dashboards pointing to different devices in your instance as well. It's also acceptable. And here I'm going to type RZ board V2L, not very creative, but again, consistency there, and I'll leave all the other options at default and hit save. This will take all of the widget configurations that are laid out within the JSON file and lay that out on what we call our dynamic dashboard. Now, this dashboard layout is easily modifiable. Once this thing completely loads, you can drag and drop these widgets around to various locations. I'm actually going to go ahead and make the screen just a little bit smaller so I can fit everything in here. And you'll notice that I could grab any of these widgets and move them around and kind of place them wherever I want. I'll leave them in the default location for today, But just know you can add other widgets using these menus down here if you'd like to customize the dashboard further. I'm currently in the dashboard edit mode, which is why we're not seeing any kind of data populating yet, and I have a save and cancel button up here. So once I'm happy with the way the dashboard looks, I can just go ahead and hit save in the upper right corner, and that's going to commit all those widgets to their fixed positions, and then begin bringing in some of the telemetry that's receiving from that MQTT feed. So now how do we use the dashboard that we have here? So let me first start off by giving a quick high-level overview. On the right, obviously, we're seeing some real-time information regarding the CPU usage, the flash memory usage, and some models that have been run as a percentage. So I did run some models here just to kind of give some interest to the pie graph here. And there's some other information about some versions. Skipping over to the far left, we have the ability to send cloud to device commands. So we can turn on any of these various demos, and we can control things like the LED on the board. So for example, if I type in red next to LED and I bring up my overlay for my board again, and I hit execute command, that's going to be sent down there, and you can see immediately the board changes to red to reflect that LED. More interesting here, though, is in the middle. I mean, this is the main meat of this presentation is about the models. So we have 4 different models that you can actuate by using these various buttons here, or again, the drop-down menu to the left. A is for a single pose overlay. We have B, which is the object classification. We have C, which is the image classification, and we have D, which is the multi-person overlay. So for example, if I wanted to start the image classifier, I can go ahead and hit the green button here. That's going to send a command down to the edge, and actually if we look at our terminal here, we can see that it received the command right here, and it's for running demo C, which is ResNet 50. So I'll go ahead and minimize that. That's going to go ahead and first stop any additional or any currently running models that are currently running, and then it'll execute the script to start the image classifier model. So it'll take a moment, and there we go. It's up and running. We can see it's active because we have image classification is now showing here. It gives some information about what to expect. It says this is an active model. We notice our CPU usage is now up in the 80s, which makes sense. And if actually I bring in my HDMI input, so this is what the RZ board is displaying right here. We can see that I have a sandal on my desk, and it is 80-some% confident that is a sandal. And I can put another object here as well. Here's a hockey puck, and it is 100% sure that is a hockey puck. So obviously there we go with the image classifier. I go ahead and remove the overlay here. So then if you wanted to switch to any other models, all you'd have to do is go ahead and click on one of these buttons here. And again, that'll go through the same process of stopping the script and starting the new object detection model. And if we go back to the HDMI view, there we go, that's fading away, and then it's going to load in the next model. So I encourage you to play with this on your own, explore the various models that are available here. And I wanted to provide just a quick recap and some further learning information here. So I'm going to flip back over to our GitHub. So I talked a little bit about using the demo, and I apologize, I'm kind of rushed due to the time constraints that we have. But again, feel free to try out and experiment with those other models. If you're looking for additional information, I have a section here where you can find some more information regarding the Linux Yocto. There's a PDF link, and there's our Avnet product page for the V2L. And you'll be able to find all the slides that were covered earlier at this link here that should be updated in the future. And some additional content regarding the IoT Connect knowledge base and overview. So if you're interested in how to create your own templates, devices, and things like that, or learn more about the platform, those links are available. So again, as a quick recap, we took the V2L board, we loaded on some custom firmware, we loaded on the IoT Connect application and configured it to talk to the IoT Connect cloud. We were able to run an AI model right at the edge, show those results in real time in our dynamic dashboard capability, and then visualize that here as well. So again, hope you enjoyed this. I know it's a lot of material to get through, so feel free to revisit the GitHub link that'll be provided after the webinar. And with that, I'm going to hand it back over to Keaton for some final words before we move to our Q&A. Thank you.